gentlemen. How are we doing?
Doing great.
Very well, thanks, Juha.
Excited for the webinar today. Excited for the spring and for the May Day Eve and all that good stuff and the topic that we have today. Like, how about that?
Yeah, it's a great way to start a long weekend, which we have here in Finland, end with a highlight.
Many things to be excited about.
Yeah, and this event at hand is actually special in a way that all of the attendees will soon see. So we have just this additional tiny element that we will be showing, which is of course the premiere of the demo video. So first time that it will see the day of light outside of the Quanscient ecosystem. So excited for that as well. But of course the broader topic couldn't be more relevant at today.
Absolutely.
But okay, I see people are joining in, so we might as well kick off the so-called official portion of the event, and that is marked by sharing the first slide deck. But don't worry, this won't take long. We'll get to the good stuff very soon. So welcome everyone to our webinar on the 3 foundational pillars of optimal MEMS design. So speaker of today, Juha Riippi, our CEO and co-founder, and our co-CTO and co-founder, Dr. Andrew Tweedie. Now, what do we have in store for you? Well, after we have watched our video, we will actually, Juha will go into what it takes to bring AI to hardware engineering. And this goes down to the 3 pillars that sort of everything revolves around here. And after Juha has gone and given the high-level overview of the 3 pillars and what they sort of mean, Andy here will go into the sort of technical breakdown of that. So what does that look like in practice? And we'll see some examples there. We'll end with a Q&A after that. But if all of this talks about these pillars and what it means and agentic simulation, all that are still unclear to you, or there is some ambiguity there, as mentioned, well, let's kick off everything with this 2-minute demo video that is the premiere of this video. So the first time we are looking at that. So I'll share it to your screens right now. And after that, as said, Juha will cover it through the sort of high-level overview, and Andy will dive into the technical details. Now, I must mention before pressing play that the audio in this is a bit loud. So if you're wearing headphones, you might want to have the audio slider at hand. So just as a bit of a warning there. But with that being said, I'll press play.
In the traditional product design workflow, simulation is a reactive tool. You ask, this is my design. How will it work? But that isn't really the question you want to ask, is it? It's time we move beyond validation to the question you actually care about. What is the optimal design for my specifications? This is the paradigm shift enabled by Quanscient All-Solve. And to make it a reality, you need 3 foundational pillars. First, massive computational scale. Quanscient All-Solve features the world's most performant cloud-native multi-physics solver. Instead of running 1 simulation at a time on local hardware, you can run thousands of strongly coupled simulations in parallel in the cloud. Second, programmatic control. Massive compute is useless if you have to set everything up manually. The new Quanscient SDK puts all that cloud power into a purely code-based Python environment, allowing you to automate simulation setups, use version control, and integrate high-fidelity multi-physics directly into your engineering pipelines. Finally, AI-driven optimization. With massive datasets and programmatic control, you can finally bridge hardware engineering and AI. You provide your specifications, and the AI agent writes the code, runs the massive design of experiments, and uses this data to train a surrogate model that can make thousands of performance predictions in milliseconds. You can now instantly identify the absolute best design and simulate how manufacturing tolerances will impact your final yield. With this process, you're no longer just testing designs. You're generating the optimal solution from your specifications and proving it can survive real-world manufacturing tolerances. Stop testing designs. Start generating solutions. Request a live demo to see how it could work for you at Quanscient.com.
All right, there we have it, the premiere of our brand new demo video. Hopefully now everyone has this basic understanding of what this is all about. And with that being said, I'll pass the floor to Juha to go into the whole topic a bit more detailed. So go ahead, Juha.
Thank you so much, Jukka. So very happy to be here, and I'll start by covering kind of a little bit on the bigger picture. So here, not talking about MEMS specifically, even though all these things apply definitely to MEMS. So some thoughts about the question, what it actually takes to bring AI to hardware engineering, and why kind of this title is that there's, all of you know and have seen the massive transformation in many industries. I come from a software background, and software development has been completely revolutionized by AI. Productivity of engineers has increased significantly, and even people without engineering background are able to build at least prototype applications. But hardware has remained pretty much the same. The tools we're using and the way of working is mostly similar as it was back in, say, 2019, the pre-ChatGPT and the LLM era. And what could be the reasons for this? Well, one of course is that the software that we use in hardware design and simulation workflow are still to this day mainly dominated by graphical user interfaces and things like that. And those are kind of difficult topics for an AI to handle, but also there's a lot of silos there. There might be organizational silos, but there also is a lot of technical silos between the different products used in different stages of the workflow. And if you look at simulation more specifically today, the workflow, to sort of caricatize a little bit, of course, some companies have more advanced workflows and more, let's say, design exploration, but typically you could still say that an engineer designs something and then you run a few simulations, a handful of simulations to validate your design. To ask the question, this is my design, how will it work? As stated in the video before. And that approach easily leaves thousands or 99% of your design space unexplored. There could be completely unorthodox designs out there that actually solve your problem better than the one that you built based on the previous products being built on your organization or kind of your experience as an engineer, something that a human intuitively does not think about, could lay out there. And then if we start looking at what would it take to expand this, to explore more of the design space and utilize AI in this, well, one, you do need a lot of compute for this. Some companies might have large on-prem clusters, but typically we're looking at the cloud. We're looking at something that can offer you this scalability when you need it and as much as you need it. Because you all know also that simulation workflow tends to be pretty bursty. So your workflow isn't, or the capacity you need is not static. So with cloud, you can really kind of exceed the limitations of on-prem clusters and go really large scale exactly when you need it. And I won't go this in order. The third step is multiphysics AI. You do need to have capability to then train surrogate models or advanced machine learning models based on your simulation data that you can train and generate when you have a lot of compute With that compute, you can go large scale, you can run large volumes of simulation, you can run more complex simulations, and now train your models with that. Today, we're focusing on the second one and the middle one, so programmatic control. So I'll cover that in a little bit more detail. And on the multiphysics AI part specifically, as you attended the conference and registered, you'll get a summary email, and that will also contain a link in our multiphysics AI webinar. So if you haven't seen that one, you can follow it from the link that you'll receive after this webinar. But when you have programmatic control, some of the things it enables is this kind of a 4-step workflow that we're proposing, which effectively means that the first step is to simulate, but not simulate a few variations, simulate a large design space, use parametric geometries, parametricize your design in multiple various ways, run a lot of different variations of your design, up to tens of thousands or hundreds of thousands of simulations enabled by the compute scale. From that data, you can train your surrogate models with simulation data that actually covers your design space already relatively quickly. And with these models, you can start exploring your design space with a surrogate model that actually runs in milliseconds, but also can do more advanced things like solving the inverse problem. So answers to the question, these are my specifications, what actually is the optimal design? And now once from this large design space, you're able to limit your options to the best candidates. Now you can again revalidate with deterministic numerical simulations. And if you have programmatic control, all of this can be controlled by agentic AI with a human in the loop to make a great engineer a 10x engineer in terms of speed of defining your models and your workflows. So programmatic access is definitely the gate. So AI can drive it, and as established, AI will not be clicking buttons in your graphical user interface. Even if it could do that effectively, it would still be slower than having a programmatic access where AI actually drives simulations through SDKs and APIs. And of course, the scale that it enables. With programmatic control and automation in place, you can run these 10,000 variations of your design way more effectively, way more easily. Combine things like optimization algorithms to really explore as big of a portion of the design space as is feasible. So, and as the third part, the code, the models you build also become an asset for your organization. As stated in the video, they can be version controlled, they're reproducible, they are not scripts that live on individual laptops of a specific engineer. They become your organization's IP, so to say, and intelligence about your designs. And if you don't have this, AI is a demo. It's not a product. But with this, that changes. And the great thing is that once you start embracing this workflow, the more you do it, the benefits compound. You gather more and more data about your design space. You gather it in a centralized place, and it's all accessible and enables even more advanced insights about your products. Like these simulations correlate exactly to this design. You have all this information at hand, and you can do very advanced data analytics on that. And of course, regardless of it being on-prem or cloud, your data is your data and your models stay yours. And you can utilize them in way more flexible ways than having simulation models on various places in your organization, on laptops, on Excel files. It'll be way more centralized. So with that, I would like to hand it over to Andy, who actually has a very practical example about a workflow like this case for a Python mechanic micromachine tool ultrasound transducer. So
yeah, thanks, Juha. So I'm going to touch on many of the points that you has covered at high level, and hopefully use an example to bring them to life and give you a feel for how you would use this in your day-to-day engineering life.
Sorry, Andy, could I quickly chime in just to let everyone know that we're talking about a lot of stuff here, and we have a dedicated Q&A at the end. But if there is a burning question, you can already park it in the questions tab in the right-hand corner. So whenever a question of anything that you see on screen comes up to your head, simply type it in the questions tab at the top right-hand corner. Only us, the speakers, can see it, and we will be covering them at the end of the event. So just wanted to put that out there for everyone. Back to you, Andy.
Yeah, thanks, Juha. And to everyone out there, your questions and thoughts are very, very much welcomed. So we've talked about how agentic workflows have the potential to make a huge impact on the way we as engineers use simulation and the way we develop hardware. And at a high level, we're really talking about the ability to automate many low-level tasks that, in our experience, take up users' time. So this could be everything from model construction to model validation, producing test cases that show that a model is behaving correctly, producing validation studies where we maybe do something like mesh convergence to understand what sort of accuracy we can achieve for a given computational cost, or indeed, as you has already touched on, starting to explore design spaces and explore design robustness using optimization techniques and Monte Carlo studies. And in addition to that, something that we are very focused on is making this a process that can be documented, repeatable, and a word we use a lot internally is inspectable. When an agent does something, how can I tell whether it is valid, whether it is what I intended and what I consider a good, robust process? And that's something we'll touch on a bit as we go. So I wanted to outline an example toolchain for the entire process we've just talked about. This is merely our choice. There are many ways that this could be done, but we find this really quite a compelling and quite an exciting way to work. So we typically use Cursor as our IDE. We, of course, use AllSolve as a powerful and very elastic multi-physics solver. As you have said, this gives us access to huge compute resources and really underpins everything that we're doing here. In the example today, we're going to use Claude Opus 4.6 as the LLM behind the agent, but of course many other models exist. Even within the Claude series, 4.7 is out now, so there are a lot of options to experiment with. And something I wanted to throw in, which is a personal choice from our engineering team, is using a task management app like Linear to not only set the task description for the agent, but actually to capture progress, comments, updates as we go. And we feel that makes it a very, to use the word again, inspectable process. And we'll touch on some of the thinking behind setting this up as we go. So the example that we've chosen from the MEMS ecosystem is a PMUT, which is something that we've done past webinars on. We've shared quite a lot of information on PMUTs, and I feel that we've shown that AllSolve is an incredibly powerful tool for the design of PMUT arrays. So we're going to create a task to create a basic PMUT model and generate some outputs. And we're going to hand this over to an agent to perform all of that. We're then going to ask for the agent to perform a mesh convergence study on the problem. And as it's doing that, we'll ask it to track all of the progress within linear. And in that way, the approach isn't too dissimilar to if one of your colleagues were working on the problem. Or an example that I use a lot internally, and I'll touch on again later, is imagine you'd given this problem to a really talented intern. For me, that's a good way of thinking about how to interact with these agents. The final thing we're going to ask it to do is produce a PowerPoint presentation so that we can share some of this information amongst our colleagues and discuss. So again, something that you would typically do as an engineer, but something that is potentially a time-consuming task. I know personally I've procrastinated a lot on PowerPoint presentations in the past, so it's a good thing to have the option to at least semi-automate the process. So one of the things to touch on at the start is the setup of the workspace within Cursor. So one crucial thing, whether it's in software development or simulation, for making good use of agents is to provide them with context. They don't have any context on the area that we're working in, the specific problem, unless we provide that. So there's a few ways of doing that. Specifically within Cursor, we find the skills feature particularly useful as a way of providing context on different operations that we frequently make use of. So we've created an AllSol SDK skill within our Cursor environment. Anytime we ask an agent to create an AllSolve model using the SDK, it knows to go and use that as a reference. And indeed, one of the nice things about Cursor is it has the built-in ability to update these skills when you encounter new features that you need or run into issues. And there are ways of doing this in essentially in all agentic flows. Some environments use an agent.md file. There are ways of providing context, but it's an important part. The other part is to create a local Python environment that we're going to work in and install the AllSolve SDK and potentially any other dependencies within Python that you might need. So for example, NumPy and matplotlib would be useful for post-processing results and creating plots. And finally, we usually provide the login credentials to our SDK in a local .env file. But again, there are various ways of doing this. So, okay, what does this look like in practice? So I've created they call them issues within linear. And it describes the task that I want to perform. So we're going to set up a PMUT cell simulation. And the description here gives an idea of the center frequency. It gives a text-based description of the stack up and the lateral dimensions. Now, clearly, if available, we could include diagrams, we could include CAD files. For a simple design like this, where the geometry is relatively simple, text works really well. Now, I've included some more details about boundary conditions and drive, a little bit too much to fit on the screen here, but hopefully you get the feel for the sort of way we're describing it. And again, this is the information that I would need to provide to one of my colleagues to set this up. So the idea is to just adequately describe the problem. And a little bit further down the issue, I've created some specific tasks. So create a unit cell model using the AllSolve SDK, run the simulation, create a local Python notebook to execute the simulation and provide some output plots, and then some information on running a mesh convergence study. And finally, some information on things I would like to see in a final report published to a PowerPoint presentation. So this is the task that we've given to the agent. And what's really nice is once you have this captured either in a local markup file, or in our case, in our linear task management app, we can simply say to the agent, can you grab this linear issue? Web1 is the tag for this. Review it carefully, make a detailed plan, and execute. And in a few minutes or so, the agent has digested the information, reviewed anything necessary, put together a plan. And for those of you familiar with Cursor, at that stage, if you're happy with it, you click build and it begins to build the model. And this is the result of the output of that process. So I asked the agent in my instructions to review everything, build the model, geometry, the physics, and the boundary conditions, and then stop at that point and allow me to inspect it before giving the okay to proceed. So the agent has given me a link to the AllSolve project, and I simply click on that. This is our physics screen where you see material definitions, physics setup, some of the variables that have been used to parameterize this. So what we have at this stage is a completely UI-driven model. It's fully parameterized via things like frequency, the excitation voltage, the dimensions. It's shareable with colleagues. I can simply click up here. There's a share option. I can send that on to colleagues. And due to all of that, it's inspectable. So if I wanted to at this point, I could take this project on myself, having allowed the agent to do some of the basic low-level work in building it. But I'm quite happy with this, so I'm going to, in this case, ask the agent to continue. So I said to the agent that I'm happy, please continue and produce the output reports that have been requested. And from this specific simulation, I'd asked for various things. So I'd asked for electrical outputs from the excitation port, including voltage, current, and charge. I'd also asked for various mechanical outputs on the front face of the device, everything from pressure to velocity. And I'd also asked in post-processing for it to calculate a transmit sensitivity spectrum and the complex electrical impedance spectrum. And those results were provided. Those were available locally in my Cursor notebook, but also were posted to the linear app. And often when I'm doing this, I actually see, the first time I notice this is I see it, I'm doing something else and I see it popping up on my phone on the linear app as an update. So there's obviously a lot of ability to automate the way you work with this. So I said that we have a UI based, a UI driven model in AllSolve at this stage, but we also have the underlying Python code that is required to generate it and run it. So this is what it looks like. Our SDK lends itself to creating quite a high level representation of the model build, and we usually give some guidelines to the agent, again in the AllSolve skill that we've created to build the model in a, again we would say, an inspectable way. So functions to create variables, build geometry, etc. So this gives us the ability to programmatically execute the simulation. We could plug this into some sort of design study or some sort of process that we already have in our design change. We could and can, obviously now that we have the project represented in code, we can maintain it through Git. So if you wanted to have a repository of examples, let's say for PMUTs, then this would be a really nice way of version controlling everything. And what's really nice is that we can do further work on this model using agents. So we could use an agent to debug the model if we notice problems, and we could ask an agent to provide additional test scenarios in order to gain confidence in the robustness of the simulation and the accuracy of it. This is something that in day-to-day engineering life we don't always have time for, but being able to say, here is my project, please go off while I'm in this next meeting and build me test cases covering these areas, is, we found, a very powerful use case for it. So to touch on that, as part of our task, we asked the agent to perform a mesh convergence study, and we've given it some guidance as to how we like to see these performed. But in this case, it's run the model in parallel on AllSolve at 4 different mesh sizes, and I asked it to track the center frequency of the device, and we can see that as the mesh converges, the center frequency drops slightly, and we've asked it to fit a curve so that we don't need to refine this to incredibly fine meshes to get a prediction of where the curve is converging to. And that allows us to estimate things like, for example, if I was to say I want my model to be set up to be 1% accurate in terms of resonant frequency, I could produce a plot like this and say that I've got some confidence that at a 4 micron mesh size, I'm going to have around about 1% accuracy. That's a really useful tool, especially when we're doing design exploration. When we're exploring design spaces, we don't always need the ultimate accuracy. We want quick ways of exploring designs. And once we've found an optimal area to work in, then we can really turn up the accuracy, use finer meshes, and get more detailed results. So building on that, many of you, I'm sure, will have heard and seen us post a lot where we talk about design exploration. It's an area that we're very interested in. And Juha touched on the high level concept of trying to solve real engineering problems what is the optimal design for this project, or perhaps what are my design options? What is the set of optimal designs that maybe trade off different design parameters that are important to me? These are the types of inverse problems that we're very interested in solving. And one of the ways we do that is to use large data sets generated by Allsolve to train AI surrogate models. And you had touched on this a little bit. It's a very rapid way of exploring a design space. And the agentic approach we've just showcased is a very effective way of doing this. So this set of optimal designs is often referred to as a Pareto front. That set represents Pareto optimal designs where essentially each design cannot be improved any further without trading off one of the design objectives. And we see that in this study here on our simple PMUT unit cell, where we have a measure of bandwidth that we would like to optimize. We have a measure of device sensitivity that we'd like to optimize. So we'd like to be in this top right corner. We've used, again, through an agentic workflow, we've said, can you generate a large data set for AI surrogate model training? We've asked the agent to train an AI surrogate to predict these things. And then we have put that model into an algorithm which locates Pareto optimal designs. And this is some work as I said, talked about before, but these are the design trade-offs. So essentially we've found designs that can operate anywhere on this line. As an engineering team, we get to decide where we want to be. And these are the representation, the actual model outputs from the dots on the line here. So we can have very wide bandwidth designs down here, or very high sensitivity designs, or anywhere in between. And we've shown that compared to the initial design that we used in this case, we were able to improve bandwidth by 35% and increase sensitivity, whilst also exactly matching the center frequency target that was set out for this design. So a really practical use of an agentic workflow. Once the model is set up, it can really automate that high-level analysis of a problem. Another thing I wanted to touch on was building on existing projects. We talked about context earlier and how that is important for any agent. But existing projects can act as context in themselves. So in this case, I've created a subtask of the initial linear issue, and I've said, I'd like to extend this unit cell model into a 5x5 array. I've provided some information on the boundary conditions that I'd like to see, because clearly they're going to be different, and where the voltage excitation should be applied. And I've asked the agent to execute it. It's created, as before, a plan, and we've very quickly run it and been able to generate this kind of quite large PMUT array model. Now, I've touched on the idea of reporting and the idea of making this whole process inspectable, repeatable, transparent even. And these are examples of some of the posts, the comments, sorry, that the agent has posted to the linear issue for these tasks. And this is obviously highly customizable. Again, we've created a skill that is linear integration, and that gives some guidelines on how we want to see. We don't want to see 20 pages of comments for each stage, because then you're just generating so much slop, if you like, that you can't actually see the real progress. I've asked for the progress updates to be quite succinct here, but it's very effective. It means that as an engineer, if you're seeing something that you don't think looks quite right, or you're seeing something that's very impressive, but that maybe needs very compelling proof that is correct, you can step in, ask additional questions, ask for additional tests and analysis to be carried out. And then finally, I asked for some PowerPoint slides to be created. I would not claim that these are the most beautiful PowerPoint slides in the world, but I would be delighted to have these produced for basic tasks to make it easier for me to communicate what's been done to colleagues. So that's a feature that we found really, or a working practice, let's say, that we found very useful as well. So I wanted to finish off by covering a couple of practical things that we've discovered along the way. I think one natural question that I'm sure people in the audience are asking is, well, what if the agent doesn't have all the information? Isn't it going to go and make mistakes? And yeah, absolutely. If you don't provide an adequate description of a task, you're unlikely to get the desired output. But one of the nice things that we've grown accustomed to when working, particularly through Cursor, is that when an agent creates a plan, it identifies missing pieces of information and asks questions, typically in this multiple choice format. So when I was originally setting this up, I didn't give any information on the extent of the top ground electrode, and this was the question I was presented with. So again, not unlike an email, a Slack message, or a conversation that you might have from or with one of your colleagues. And then finally, as a tips and tricks, this is something I touched on earlier, but treat the agent like a very capable intern, and I think things will go well for you. So the way I look at it, and the way we look at it within Quanscient, is it can solve very complex problems for you, problems which, if you don't have the deep domain knowledge in, might be hard to digest in an afternoon's worth of work. This is excellent, but clearly we can't expect an agent to have context and the background knowledge of how you do things within your organization, how you plot particular charts. So being explicit, building in instructions, and questioning everything is a really good practice. And when it comes to that context, I think I touched on this a little bit. If it's problem specific, then the problem description, the prompt, or the task description that is being given to the agent is a great way to capture it. If it's something very general that applies to all of your work, then including it in a skill, if it's Cursor, or in general, some sort of markup file, agents MD, is ideal. That way you'll get consistent results across various projects. So to conclude, we really feel that the SDK is a very powerful tool for unlocking this kind of workflow for hardware engineers. It allows really enterprise-grade multi-physics simulations to be built and tested in a very automated way, while giving engineers time back in their day and allowing us to focus on higher level, perhaps more creative tasks. And this is something that we internally as an engineering team within Quanscient are seeing a huge impact of. And the thing I'd like to really emphasize is that when done properly, the work is documented, it can be tested, it can be very inspectable. And I think if done properly, often to a higher degree than work that is picked up by busy engineers who have many things to juggle. So in my opinion, definitely not a party trick. And it's something that we're beginning to rely on quite heavily. I'm sure that you all have interesting thoughts and questions, so we look forward to discussing that in our forthcoming Q&A, but most importantly, we would welcome you to reach out if you're interested in finding out more about using agentic AI in your workflows and indeed adopting these types of processes.
And with that, I have launched this quick little poll that you can simply click, that if indeed what you just saw there was something that was interesting to you, something that you would like to learn more about, just explore further how that could benefit you, your task, your job. Then you can simply click on that button, click on those buttons right there, and we'll take it from there. So I'll just let this be on the screen for a while. In the meantime, there was actually the first question, which basically asked that this person's company has preferred software and a software stack. And the question was that if you were to want to run this on different software, let's say Visual Studio Code, or use a different AI, so is that possible? So sort of a recap question, but
great question. Absolutely. As I mentioned, we've chosen that stack because these are the tools that we use internally. Our software development team uses Cursor. This with Allsolve's Python SDK, this process could be really integrated into any stack. So no limitations on that front.
All right, thank you. I'm ending the poll, and thank you everyone for your responses. But as mentioned, and you can always reach out in other ways. So if you didn't answer this poll, you can always reach out in other avenues as well. So thank you, Andy, for your presentation. Thank you, Juha, and let's use the following 12 minutes or so for the official part of the Q&A. So the next question was, and I'm quoting, so the idea would be that more AI agents interact with each other and create and solve what we prompted, right?
I think that is definitely the direction that I'm interested in going in. And some of that's natively supported in Cursor. So when you create a plan, like I showed, they've changed that a little bit over the months. Software in this area is iterating very quickly, but there are options to assign subtasks to agents. So yeah, that kind of parallelism to break projects into subtasks and assign them is very much possible. I know that there are frameworks where agents can collaborate and interact with each other as asked in the question. I've not personally explored that, but I know that there's a lot of work on that. And then the other thing that I would just flag up on the back of that question is, I've talked a bit about assigning something to an agent and allowing you to go and get on with your day job, perhaps take a meeting, perhaps work on another task. We're implicitly not talking about something that you sit over the IDE and watch every line as it's generated. But on top of that, that opens up the possibility, if you are doing some focused simulation work, of running multiple projects at one time. So very much possible to have multiple sessions, each focused on different projects. Again, to use the intern analogy, it's like having different interns coming back and reporting to you on their progress. So there's a lot of flexibility throughout all of that. And I think we're just starting to scratch the surface on what's possible there.
Yeah, and maybe not directly related to this, but just to highlight kind of on the versatility. So of course, this what Andy just presented, kind of all the automation and having agents define your simulation workflows. But we've also internally done things like building a completely custom user interface on top of the AllSolve SDK. So let's say, for example, well, what would be the value of that? One of the things we've been thinking is that companies often might get, for example, requests for proposals in the sales. So if you had well-trained surrogate models on your design space, this could significantly speed up responding to those RFPs, because you could immediately kind of with a customized UI or scripting or with agents immediately simulate if the customer request is feasible and what kind of design changes might we need to do that, or do we have something that kind of works out of the shell. So just one example, but of course also for, say, the engineers who are not expert in simulation tools, this could sort of democratize a lot of things, because you could build, well, for example, customized UIs where they only need to manipulate the design parameters that they actually care about. So just to sort of broaden the horizon, and with agentic AI, we built these custom UIs in less than an hour, basically full stack that runs the simulations then in the backend in the cloud.
Well, then basically a question that ties into the nature of AllSolve itself. So basically running thousands of simulations to generate these training data sets sounds amazing, but does running 10,000 simulations mean we blow our entire software budget in one day?
Not necessarily. I think we've presented various webinars which show this workflow. In the case of the PMUT cell model that I showed here, I think we generated a data set of 10,000 simulations, and the cost was in the order of maybe a couple of cups of coffee, to use that as a metric. So of course it's quite a simple model, and obviously the cost is higher for much larger, many tens of millions of degree of freedom multiphysics models. But it's certainly feasible in many of the problems that we focus on.
All right. And then how about on the sort of fundamentals of utilizing this Python, this SDK? So if someone is sort of very used to the GUI and clicking on menus, and they see this Python, they see this SDK code and find it a bit overwhelming. So how good of a coder or a programmer do you have to be to actually run these end-to-end workflows via this SDK?
Do you want to take that one, Juha?
Yeah, absolutely.
You've talked a bit about this.
Yeah. So definitely you don't have to be a software engineer or programmer to do that. And there's a few things that really help there. So one is one workflow that's very helpful is that when you define your simulation models using the AllSolve GUI, it actually automatically generates you a Python script. That is your simulation model. Now you can use that as is with the SDK, and then all that the SDK actually needs to do is kind of the coordination on how many cores are you running it on and so forth. So kind of what's surrounded from the actual simulation model. And that's a very simple script. And most AIs can handle that part very easily. And of course, we have a lot of examples and tutorials on that as well. So it's really easy to get started with it. Which also maybe refers, there was a question that is Claude Opus required for all situations, or is Sonnet useful in the workflows, as Opus is more costly? So no, definitely you don't need Opus. But if you, let's say, if you want to do more advanced model building, more kind of something that requires in a way a smarter, higher capable model, then typically Opus performs better. But if you want to write the SDK code, these lower tier models should handle just fine as well.
I absolutely agree on that one, and I think I was really glad that someone asked that question. Yeah, I've had a lot of success with much smaller models, much more cost-effective models, and I think on the topic of skills and context, the more that you can build in that awareness of the features in the SDK, the way that you want to approach these simulations, the more you can point to, here's a previous project that went really well, do this, but for a different case, you can start to rely on much simpler, more cost-effective models. And certainly my hope is that the LLM cost or the agentic cost of this is not a big bottleneck for people wanting to utilize it.
Okay, we have about 3 minutes, so we'll have time for the last question and perhaps short answers from both. So with the state of AI being as it is right now, and the SDK and also cloud compute capabilities, and basically all of these technologies, especially the AI technologies, are advancing further and further, where do you see and how do you see the engineering day-to-day work move and evolve in the next year, 2 years, or short-term future?
I can say personally that my day-to-day engineering workflow has changed substantially in the last 6 months. I think tasks that I would previously have taken on completely manually, I routinely use the sort of workflows that we saw today. I think moving forward, the challenge is how to do that at scale. How far can you go while maintaining the quality and the validation and the repeatability? Hence our focus on logging and documentation. So there's certainly huge potential for it, and I would love to see a future where graduate engineers are simulation superstars and are genuinely able to work at many times the previous level.
Yeah, and maybe to add on my part on this, I recently built a PMUT simulation. My background is software engineering. I don't understand anything about PMUTs, but with the help of AI AllSolve, I was able to do that in 15 minutes. It was checked. It actually makes sense. It's a pretty simple simulation, but so yeah, if I'm able to do something like that extremely quickly, what can the people who actually know what they're doing in the domain area can achieve now? Not to even mention 6 to 12 months from now.
All right. Well, thank you everyone, thank you, Andy. Thank you, Juha. Thank you, all of the people who joined. I see we are out of time, so we'll have to reconvene next time. So have a great day, everyone, and we'll see you again.
Thanks very much, everyone. Bye-bye.